Hello, this is my take on GPT-like language models. I'm going to talk about two things, how they work and also consequences for society. And obviously nobody knows what the consequences for society really will be. So that's why there's a little smiley here. You have to take what I say with a pinch of salt. So my contents here are, in the first half, I want to talk about how these things work. So how GPT works and how ChatGPT is GPT plus some other things. And that's the technical part. So please feel free to skip ahead if you're not interested in the technical part. It's from slides 1 to 10. The non-technical part begins on slide 11. And down here, as you can see, there's a slide counter. So we're on 2 out of 23 here. So you can just skip ahead in the video until it says 11 out of 23, and then you'll get the non-technical part. And in that part, I'll talk about the limitations, the consequences for computer security, and then also the consequences for society as I see them. So let me start with the core algorithm then. The core idea of GPT is an algorithm that takes as input a sequence of words. So here we have n-1 words, and it computes a probability density function for the nth word, for the following word. And then it uses the probability density function to pick that nth word. And now we have a sequence of n words. We can repeat that procedure to get the n+1th word and then the n+2th word and so on. Immediately, just in that little explanation there, you can see that there's going to be an important parameter, which is called temperature, in fact. So if temperature is 0, then in this second step, we will pick the most probable word according to that probability density function. And if you do that, then you get flat, boring, and repetitive text, which is quite predictable because it's always picking the most probable word. So what you can do is you can raise the temperature. As the temperature approaches 1, it chooses less and less likely words. And as it approaches 1, you'll get wild, crazy, random associations. And it turns out that setting the temperature at about 0.8 is the right balance between predictability and an element of kind of progression in the text. So it's not just repeating things that have been said already. Let me just mention, it's quite a challenging problem to solve. First of all, n is large, so the number of words you take as input to this algorithm, that's the n here, is about 2048. And that's a large number. It's difficult to build a model that can reason with such a big sequence as input. And part of the reason for that is that the sequence that you're taking as input does not occur in the training data. So remember, the training data is everything that GPT has been trained on. So that's most of the stuff out there on the web and probably a lot more stuff as well. So billions and billions of words. Even though there are billions of words, if I take an arbitrary sequence of size 2048, it's very unlikely that that particular sequence appears in the training data. And therefore, the algorithm is going to have to work with some kind of similarity metric. It can't just rely on those particular words appearing in that order in the training data, but it's going to look for similar sequences or subsequences of these input words. And therefore we have to, when designing this algorithm, we have to have some notion of similarity. I'm going to explain how that works. Then another challenge that you have here is that the structure of a sentence is not just given by the syntax, which would be complicated enough, but it's also given often by the semantics. And here's an example. So an AFRA resolution is about how you decide what a word like she or he or it or her or his refers to. And here you have two sentences where the word she is referring to different things in each sentence, even though the sentences are grammatically very similar. So the first sentence is, Margaret invited Susan for a visit, but she was being insincere. And I think most people would agree that the she there refers to Margaret. It was an insincere invitation. In the second sentence, which is grammatically very similar, it says, Margaret invited Susan for a visit, but she was busy. clearly there the she refers to Susan. It doesn't make sense to say that Margaret was busy. It's obviously that Susan was busy and therefore declined the invitation. So the point here is that the structure of a sentence can be semantic. It can depend on the meaning of those words, on the words insincere and busy. And GPT is going to somehow have to cope with that kind of issue as well. And there are many, many more issues if you think about the way sentences work that GPT has to cope with. Okay, so the first core concept is the so-called language embedding. And a language embedding is a function which takes a word, so we've got 40,000 words in the vocabulary here. It takes a word and it returns a d-dimensional vector. Here d is, again, that number 2048. So we're going to return a vector of length 2048, a vector of real numbers. And the idea is that two words, x and y, will be similar in the mapped space. They will be cosine similar as far as the vectors are concerned, if and only if they are syntactically and semantically similar in ordinary language, the way we use ordinary language. So for example, if you look at alligator and crocodile, in this embedding, of course this is just a two-dimensional, we know that it's really 2048 dimensions, but here we just imagine it as two dimensions so we can see it on the screen. And alligator and crocodile being words that are very similar from the way they are used, so often people might even use them interchangeably, alligator and crocodile, therefore they map to very similar vectors in this vector space. But other words like blackberry and eagle, they're obviously very different concepts and they're far from each other in this vector space. So here you have, for example, a bunch of fruits, and here you have a bunch of animals of various kinds. And the idea is that words are close to each other in this vector space if and only if they are syntactically and semantically similar. And the idea now is that this allows you to do this kind of reasoning. Let's imagine we take the embedding, according to this embedding function, of the word Madrid, and then of the word Spain. Now these things are just vectors now. They're vectors in this d-dimensional space, so we can add and subtract them. Suppose we take Madrid, the vector for Madrid, and we remove, so we subtract the vector for Spain, and we add the vector for France. What word do you think we might be close to here? Well, the idea is that we're taking Madrid and we're removing the part of it that pertains to Spain and adding a part that pertains to France, and therefore we should get Paris back, because Spain relates to Madrid in the same way as France relates to Paris. And here's another example. If I take king and I subtract the male part of it and I add a female part of it, so I kind of convert king from being a male to a female, then of course I'm going to get queen as a result. If this embedding function is behaving properly, if it is giving us a similarity that matches the syntactical and semantical similarity of the words in ordinary language. So now, how can we find that embedding? That's a huge thing. Obviously, you couldn't expect to design that manually. You couldn't expect to kind of somehow come up with the 2048 real numbers that go in the vector for every single word in that 40,000 words. It's just not possible to do that. We don't even know what those dimensions are meant to mean. We could assign meanings to them, but the whole idea of machine learning is that you don't have to do that. They will just get discovered during the training process. So how is that going to work? Well, as mentioned, we've got this function e that maps v to this d-dimensional vector space. So we've understood that. And then I also mentioned we have this generation function g. The idea of g is that it's going to give us back, for a sequence of n words, it's going to give us back a probability distribution over the vocabulary. Now, instead of feeding words to it, we're going to feed those embeddings. So we're going to give it the flexibility to substitute different words that are semantically and syntactically similar. And that's how we're going to capture this ability to generate text that is not part of the training data. So we have these two functions then, E and G, and we're going to have to figure out what they are. So let's look at how they might be defined. Well, E is the embedding function. So essentially, it is a vector for each of the words. So here's the vector for the first word, here's the vector for the second word, and so on. Here's the vector for the last word in our 40,000 words. So this matrix has 40,000 columns in it, and it's got 2048 rows because each of those vectors is of length 2048. And therefore in total it's got about 80 million parameters in E. We need to learn the values of these parameters in our machine learning algorithm. And then G is going to be designed as a neural net. In fact, it's going to have billions of parameters in it. And we're going to look more closely at how G is defined as a neural net using this methodology of transformers in the next slides. But already with what we've got, we can see this now as a machine learning problem, because we have two functions with between them billions of parameters that are needed to be learned from training data. And what will be the criterion for deciding these parameters? Well, it will be the probability of that training data matching the parameters that we've discovered. We want to maximize that probability. We want to maximize the probability or the likelihood of the training data T. So imagine we have some training data. It is billions of sequences that we are going to train on. And what we do for each of those sequences is we look at the probability that that sequence will give us the following word in the training data. And then we multiply all those probabilities, or if you like, we add up the logs of all those probabilities, and that's the thing that we want to maximize. And that's a classic machine learning problem. Machine learning is all about doing that kind of thing, and we know many algorithms that will help to do that once we have decided on the structure of G. So how to construct G is the question that we now face. How to construct this neural net with billions of parameters. Well, let's look at how neural nets work. So I assume that you're almost certainly already familiar with how neural nets work, and therefore you know that the fundamental calculation in neural nets is a calculation which, given an input vector, let's say an input of length n, it will output, this particular layer will output another vector of length m. And the one thing neural nets know how to do is multiply by a weights matrix and add a bias. So we get wx plus b, where w is the weights and b is the bias. And by the way, I don't mean bias in the sense that AI is biased. That is a real life concern, of course, that AI is biased. But here I'm talking about bias in the mathematical sense. The bias of a function is the value that the function takes when the argument is 0. So it's nothing to do with the bias in AI. The fundamental algorithm in neural nets, the fundamental operation is we take an input, we multiply it by a weights matrix, add a bias, and then we put it through this activation function, which is a nonlinear thing. That's very important in neural nets. We get out this output y. So we take n inputs, munge them around in the way I just described, and we get out m outputs. So that's a single layer. A deep neural net is, of course, lots of those layers just piled on top of each other. It's deep in the sense that there are a lot of them. And the one I've drawn here is dense because every input is connected with every output. Well, it might not look like that in the picture, but that's what I had in mind. And in general, we don't want neural nets to be dense. We want to find ways of making them not dense because that will make them computationally simpler. But the challenge is to make them not dense in the right sort of way, in the way that matches the application that we have in mind. And then the other way we have of reducing the computational complexity in such a deep neural net is to share weights, this W matrix and the bias matrix as well. So we share weights and biases. they should be shared across different parts of the neural net. That will make the neural net smaller and the computation more efficient. So how do we do that? How do we address this challenge? Well, for example, in the case of neural nets that classify images, the answer to that is we use convolutional neural nets. We use a particular structure of the neural nets that matches the application at hand. And because images are these two-dimensional raster spaces, the value of the pixels arranged in 2 dimensions, it turns out that these two-dimensional tiles that travel across the picture is a good way to do it, because we minimize the number of, or we reduce the number of weights that we would have if we used a dense neural net, and hence we make the whole thing more efficient. So we're looking now for the similar thing to do in the application at hand here, which is the application of language models. Well, the concept that is going to guide us has been called attention. So the fundamental concept that will guide us here in designing the structure of the neural net is this notion of attention. That's the name given to it in this paper called Attention is All You Need, and these 2 figures are pulled from that paper. I actually prefer the word relevance to attention, because what these structures are showing us is the relevance, according to certain criteria, of different words to each other. So I say according to certain criteria because there are many copies of this relevance structure or attention structure in the neural net that we're going to design. There's hundreds of these copies, and each of them is pulling out relevance according to a different aspect. So here, this first one, for example, seems to me to be about the structure of the sentence. See, in this picture, it's divided it into the kind of grammatical components of the sentence. So you have a noun phrase here, the law, and then you have a verb phrase, will never be perfect, and those are related to each other according to these red lines. And then another noun phrase, its application, and then the corresponding verb phrase, should be just. These, in this picture, of course, the heavy lines have a big weighting, and the paler lines have a lighter weighting. And it just looks like this is pulling out the structure of the sentence, the noun phrases, the verb phrases, and the other grammatical components in this way. Whereas the one on the right seems more to be about adjectives. So, for example, perfect here is an adjective, and it is clearly relating to law rather than any other word in that sentence. And then here the concept of being just, that is related to the application rather than to, again, any other noun that appears in this structure. So it seems to be more semantic, and this one more syntactic. But that's just what seems to me, and perhaps to other people. We don't know what the neural net is actually doing. As always with neural nets, it's doing its own thing, and it's quite hard for people to look into it and say, oh yeah, I see that this little bit of it is doing this or that. In general, you can't do that. You can try, but it doesn't work usually. But anyway, the point here is that this concept of attention, or as I call it, relevance, is going to be the main guide in how we should build the neural net at hand. So I want to come to that, and what I want to do is I want to reconstruct the way the construction of G works. And it's taken me quite a bit of time to do that, because if you look in the literature and you kind of read about it, and there's lots of papers about it and explainers and so on, they all kind of give a similar account, but it looks so arbitrary to me. I couldn't understand for quite some time why it is designed like that. And then finally, I figured out that it's inevitably designed like that. It's quite canonical, the construction. There's not that many alternatives in the big picture. So I want to explain now why I think this construction of so-called transformers is actually inevitable, if you want to be guided by this attention or relevance structure. So here goes. We were designing G, and we have an input. The input is called X. What is the type of X? Well, it's n d-dimensional vectors. So it's a matrix with d rows and n columns. And we are a neural net. So what are we going to do with that input? Well, there's only one thing a neural net can do, and that is wx plus b, multiplied by a weights matrix and add a bias matrix, and then put that through an appropriate activation function. So we do that, and then here you see we're constrained now because x has type d times n, this must be of type d times d, this must be of type d times n as well. So that's the first thing we do. And then the next thing we do is we want to build in the attention matrix now. And we know that the attention matrix is an n by n matrix. We saw that in the previous slide. It gives you a weight for each word to each other word. There are n words, so it's an n by n matrix. Now, are we done? Is that the end of the construction? Because we have parameters in here, we have parameters in here, and now we can kind of add, we can layer these things. We have parameters in the attention matrix as well. But no, we're not done, because the attention matrix, that's an n by n matrix, it depends on x. In fact, for each cell in A is a function of two word embeddings, two columns of x, if you like. So to construct A, I need two copies of x. Now let's look at how we can construct A from those two copies. Well, we are a neural net. There's only one thing we can do with our arguments, and that is wx plus b of them, because that's what neural nets do. But of course it will be a different w from the one we used previously, and this one is a different one again, and the b is again different. So here we subscripted by k, which stands for keys, and we subscript this one by q, which stands for queries. And I don't think those keys and queries words are that important. I just reuse the symbols there, k and q, to kind of match with the literature. But essentially we've got a new set of weights and a new bias here, and then another new one and new bias here as well. Now we're trying to construct A as an n by n matrix out of this. So what can I do? Well, I could multiply these things together, but first I have to take the transpose of the first one, so that it's n times d instead of d times n now. And then now the result will be of type n times n. So I'm done, almost. I'll just put in a column-wise softmax to scale things, and then that will be my definition of A. And that is the entire thing. That is a self-attention transformer block that maps x to y as follows. It takes the x, it does a simple neural net calculation of it, and then it multiplies by this matrix A, which also depends on x and is constructed in that way that we just saw. And that's it. It seems to me that there wasn't many design choices we could have had in there. We had to kind of do it that way. That was the obvious way to do it. We just kind of followed our nose, as my friend Roland likes to put it. That's it. That's the self-attention transformer block. And here's a picture of it. So it just takes an input x and it produces an output y, and I'm wrapping up in this purple block all of that computation that's being done. And of course the whole thing is parameterized by d, the number of dimensions, and n, the number of words in the sequence that we're processing. And those are of course the type of this input x. Now the whole construction then is what I just described there, but what they do is instead of processing all of the dimensions at once, they process them in blocks. So they decide a certain number of heads, as they're called, and that is the number of blocks of this D that they process at a time. So what you end up with is called a multi-head self-attention transformer. You have multiple heads here, each of them processing a part of the 2048 dimensions that we have. And that obviously very much reduces the number of parameters that we have in here, because instead of having a huge attention matrix, we end up with a smaller one. So we have this multi-head self-attention transformer, and there's two other parts to it that I'll just briefly mention. There's a scaling part of it, and then there's a neural net or n neural nets that process each of the words in the sequence separately. So we have an n times process going on here, and then another scaling. And that is the multi-head self-attention transformer, and then we have multiple of those. So we stack those up with hundreds of layers of it, and of course there are hundreds of heads going in the vertical dimension. So this thing has hundreds times hundreds copies of this multi-head self-attention transformer. So that ends my description of how multi-head self-attention transformers work. And hence now we know how it computes the next word from the sequence of words. I want to just say a few things about what ChatGPT is as opposed to GPT. Well, it's several things, of course. The first thing, fundamentally, is what we just described, namely a next word language model, which has the capability, when given n-1 words, it has the capability of finding the nth one that's syntactically and semantically plausible. By the way, it's worth just pausing there and noticing that there's nothing in what we've said that says that the output of this thing will be truthful. It will be plausible. It will be plausible in the sense that we could imagine a human could have said such a thing. But there's nothing in that construction that gives us any guarantee that the output will be a true statement. Simply that it will be a syntactical and semantically plausible statement. So that's the first part of what GPT is. Now the second part is called multiple shot processing. And if you've played with ChatGPT, then you've kind of experienced that, because you can condition on examples. You can say, do something like this, and then it will understand what you mean from the example and apply it to the other situation that you described. And we also have in ChatGPT chain of thought reasoning and conversation following. Those are kind of layers that are added to this next word language model. Then another very important thing in ChatGPT is so-called reinforcement learning from human feedback, RLHF. And what that does is it allows the designers of ChatGPT to use humans when given two GPT answers to a certain question. Humans are asked to say which one is preferable. And then that feedback from humans is used in the design of the reinforcement learning part of GPT, where it selects from several different answers that it could give. It selects the one that most matches what humans would say is a preferable answer. Now that's very clever, because obviously asking humans to decide which answer is preferable is only affordable on a very small scale. I mean, even if you can afford to do tens of thousands or hundreds of thousands of this, it's nothing compared with the billions of parameters and billions of words of text that the whole system has been designed with. And that's because anything that involves humans is, of course, very expensive and takes much longer than stuff that can just be done by machine alone. So the clever part of this is that they have a technique to learn a reward function in the sense of reinforcement learning from this small number of human answers. And then the last part of ChatGPT that I will mention is what I'm calling its censorship jail. It censors itself. It doesn't talk about any topics. There are some topics that are forbidden. For example, if you ask it how to make a bomb, it will politely reply telling you that it can't give you that information. And then another part of its censorship is the toxicity avoidance. Some machinery which enables, which prevents it from making racist statements or sexist statements or other undesirable output of that kind. So it really is an incredible thing. Everyone knows that, and I don't need to add my own words to say that. But I want to instead focus on some fails in ChatGPT and in GPT, therefore, because I think that will help us understand better what it's good at and what it's bad at. And this is just my personal list of fails that I've kind of noticed as I've been experimenting with it. So the first one is that it can prove statements which are false, like the statement here that if p is prime, then p plus 2 is also prime. That's obviously false. There are many, many counterexamples to that. And yet ChatGPT will cheerfully come up with a plausible looking proof. And it really is plausible looking because it says that if p is prime, to prove that if p is prime, then p plus, to prove that if p is prime, then p plus 2 is also prime, we're going to proceed by proof of contradiction. So suppose p is a prime number and p plus 2 is not a prime number, and then we're going to derive a contradiction from that. And if you kind of skip ahead, therefore, you see this contradicts our assumption. And then here again, this contradicts our assumption. So both possibilities lead to a contradiction, and therefore we can conclude that if p is a prime number, then p plus 2 is also a prime number. It looks like a perfect proof at first glance. But if you look into it a little bit more in detail, you see that there's something very odd about this contradiction here, because it says if p equals 2, then p plus 2 equals 4, which is not a prime number. This contradicts our assumption that p plus 2 is not a prime number. Well, hang on, no it doesn't. It confirms our assumption. We've concluded that p plus 2 is not a prime number. That does not contradict our assumption that p plus 2 is not a prime number. It's just got that wrong. It just doesn't quite understand how to do a proof by contradiction, or what a contradiction really is. And therefore it's come up with what looks plausible at first glance, but is plainly false. If you go away now and ask ChatGPT to do this, it will probably come up with a different proof, but of course one that is also false, although hopefully equally plausible when kind of viewed from a distance, just like this one. But sometimes it might come up with something else. Here I asked it essentially the same question, and it says this statement is known as the twin prime conjecture and has not been proven or disproven so far. Therefore, it's not possible to provide a proof of this statement. Well, there is something called the twin prime conjecture. That's the conjecture that says there are infinitely many primes p such that p plus 2 is also prime. But that's not what we asked for here. We asked it to prove that all primes satisfy that rule, which is a plainly false thing. And therefore, it's given us something that is kind of relevant to the question, but does not address the question. And that's just one of its failings as well. Okay, let me just focus on some numerical calculations. If you ask GPT what 2 times 2 is, it gives the right answer. If you ask it what 841 times 625 is, it also gives the right answer. But if you ask it some larger numbers here, the product of these two large numbers, it comes up with an answer which is not completely ridiculous, but is not correct. It's just wrong in some of the lower significant digits there. And if you ask it to try that again, just repeat the question, it comes up with a different wrong answer. And what's interesting is the answers are not completely absurd. They're in the right ballpark, they just happen to be wrong. Now, why is that? Well, the reason that that's happening is because it's not actually doing a calculation. It doesn't know how to do calculations. What it's doing is just looking at what is the next plausible word in the sequence of words that we have so far. And by the way, I should point out here that although in the earlier part I described those things as words, it would be more accurate to describe them as tokens, because they might be fragments of words or digits from a number or punctuation or any such thing. All those count as tokens, and the fundamental algorithm is working at the level of those tokens, not of words as we know them. Now, if I ask it the sum of those two things, then it comes up with the correct answer. But if I ask it the sum of two larger numbers, then once again, it's able to come up with an incorrect answer. And this one's very interesting because it's incorrect for a curious reason. Interestingly, GPT says, well, the answer is such and such a number, which is a 19-digit number. But the actual number of digits here is 16, not 19. It's a 16-digit number that it's come up with, even though it says it's a 19-digit number. The actual answer is a 19-digit number, and it's the answer that GPT gave with 3 further digits appended to the end. So GPT has done quite a good job of coming up with the answer in the sense that the first 16 digits are correct. It just happens that it's left off the last 3 digits. And if you think about it from the point of view of a language model, that might be quite a reasonable output, but of course numerically it's wrong by a factor of 1,000. So it's completely inadequate from a numerical perspective. And then my final example here is if you ask it to add some really large numbers, then curiously it comes up with the answer, I'm sorry, but the numbers you provided are too large to be added accurately by a computer program. The sum of those things is a very large number and it would require specialized software to perform accurately. Well, that's really strange because it's kind of behaving as if it was, in the previous examples, actually doing the computation. And of course, it's not actually doing the computation. We see that. So why it says it can't do this particular computation, I don't know. Okay, another example I just want to describe here is something that happened to me. I was looking at this concept of defense in depth in information security. It's a very well-known kind of idea in computer security. We should have defense in depth, but I was struggling to find academic sources. There's plenty of sort of anecdotal or blogs or whatever that talk about it, but I wanted some academic papers. And I looked on Google Scholar and I looked elsewhere, just couldn't find any academic papers. So I thought, why not ask GPT? And I was very impressed by the answer at first, because it said, well, here's a paper called The Science of Defense in Depth. Well, that sounds a good title, by Matt Bishop, who's a known person in computer security, in the proceedings of the ACSAC conference 2005. That's a well-regarded conference. So this paper is perfect for my purposes. It provides an overview of the science behind defense and depth information security, including benefits and blah, 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 blah. So that's great. And then this second paper looks just as good. A survey of defense in depth techniques, again in a known conference and with a very, very useful looking description there. And this third one is in the Communications of the ACM. That's a well-respected industry magazine for computer science academics. Great. But when I went to look for these papers, I found that they are all fictitious. This paper just doesn't exist in that conference proceedings, and this one doesn't exist in that conference proceedings. In fact, none of these papers exist anywhere. GPT has just made up something that looks plausible. And indeed, why not? I mean, that's exactly what GPT does. It constructs sentences that look plausible. That's its job. There's no reason to believe that what it says is truthful. So let me just give you one more example of that. I asked GPT, who is Guilin Wang? Guilin Wang is a researcher in computer science. He works for a company in Singapore, and he works in the area of computer security and cryptography. It says Guilin Wang is a computer science professor and researcher who specializes in the field of cryptography and security. Well, that bit is correct, but he's not a professor in computer science at University College London. He's never been or attended University College London, and he's certainly not the director of any centre in UCL. He did, however, get his PhD in the Chinese Academy of Sciences. It could well be around 2002, so that bit could be correct. This is just a mix of correct and incorrect stuff about this person. And the point is, GPT does not have to be truthful. There's nothing in its design that tells us it's going to be truthful. It just has to be linguistically plausible. Another example here, this is my last example. but obviously quite a controversial one, because here is a professor in American law department who GPT says was cited as being assaulting students on a certain trip to Alaska, working at a certain law department, and that there's a Washington Post article that says that. And the whole thing is wrong. He never went on such a trip, he never taught at this school, and there is no Washington Post article that says he did. GPT just made up something that's linguistically plausible, but untrue. Okay, well, those are some fails. Now I want to look at some impressive examples, and of course there are many more impressive examples than there are fails. I wanted to look at the fails because I wanted to emphasize this point, that what GPT comes up with, the criterion that GPT is applying is plausibility, not truthfulness. So here are some impressive examples which show that GPT really is useful and does a very good job at certain things. The first one, so these are kind of a bit technical, they're oriented towards programmers and people like that. The first one is that you can tell GPT to make your program secure. And this is an actual example that I did just before I recorded this talk. Here I've got a little Python program which asks the user for some input and then executes a system command called grep, which is looking up the input in a file. So it takes some input and it looks that input up in the password file in this case, and it gives you back the result. Now, anybody who has been trained a little bit in computer security would be able to say, well, that's insecure. It's insecure because we're taking user input and then we're executing a command that includes the user input in such a way that the user could put in their input some further commands, and those will be executed as well. And that's bad, because that means that the user can execute an arbitrary command on our system. That's insecure. So we tell GPT, make this code secure. We just give it that code. And it comes up with a perfect answer. The answer uses the subprocess module instead of the OS module, because the subprocess module is able to specifically call the function that we want, called grep, with certain arguments, in a way that can't be commandeered by the user to execute other commands. This line will only execute grep, and it will do so on the user's input, but it will not execute any commands that are contained in the user's input. So that's the first way in which this is more secure. And the second way in which it's more secure is that this program validates its input. It will reject input that is not alphanumeric. So it has these two checks on the user's input to perform its job more securely. And this would be an enormous help, because there's lots of code out there which is insecure, and programmers who maybe aren't well enough educated or just can't be bothered to make it secure could now do so very easily. They can just pipe that to GPT and it will give them the secure version of their code, and it greatly simplifies their job and hence improves their ability to write secure code, which would be very good. My next example, again in the area of programming, is if you're trying to understand a program, you might be faced with a function call and you just don't know quite what that function call is doing. You might have a few intuitions about what it's doing here. For example, this is something to do with k nearest neighbor, but I don't know exactly what all these arguments are. Well, let me ask GPT, and GPT figures out, again, with plausibility in mind, and that's all it can do here. I just want to know what, because it doesn't know what the library is that I'm calling here. It's just going to be guided by the names of the variables. But it knows more about k nearest network and libraries and all. Sorry, k nearest, whatever it's called, KNN. It knows more about that than I do, and therefore it's able to come up with with a very useful statement about what these arguments are probably doing that I can come up with by myself, and that enables me to explore this code much more efficiently than I could do without GPT. Final example is I maintain a website. It uses a framework called Hugo, which takes code like this and produces static HTML pages. And I was struggling I wanted to iterate through all my Hugo pages and select those that have a field set and then display links to those pages in a certain way. But I couldn't just get that bit where I want to iterate through all the pages and select those that have a field set to a certain value. And you struggle with these things on Google, and you look at Stack Overflow and you find lots of people proposing or asking similar questions which aren't quite the same as your question, and you try to kind of adapt those. Well, after about 20 minutes, I thought, why don't I just ask GPT? And it came up with the perfect answer. I just copied and pasted this into my code and worked first time. And I think that's a huge application of GPT. Okay, so let me explain in my last few slides some of the consequences as I see them. And I want to first talk about the consequences for computer security. So in computer security, you have defenders and attackers. And one thing that's interesting to note is that defenders have to be right all the time, whereas attackers have to be right only some of the time or only once. The reason for that is that defenses have to work always, whereas an attacker, it's enough if an attacker will be happy if the attack succeeds just a few times. So just to see an example of that, consider the problem of spam. If you are a defender, so you're writing spam detection code, your code has to be right all the time. Your users will be cross if you have false positives and if you have false negatives. So you've got to get it right all the time. Whereas if you're an attacker in the spam space, then you don't mind sending out millions of messages even if only 1% of them actually have the desired effect. You just have to be right a few times. It doesn't matter if you're wrong most of the time, because it's just those few times that you're going to get a successful attack, and that's what's going to work for you. So because AI is fundamentally a heuristic technology that is not right all the time, it's just right some of the time. We saw plenty of examples of that in the talk so far. That means that AI generally helps attackers more than defenders. And that's a very sad thing. Because attackers only have to be right some of the time, they can use methods that are based on heuristics, whereas defenders will find it much more difficult to use those things because those methods just aren't right often enough. Anyway, I mean, having said that, there are some examples that we've already seen where GPT will enormously help defenders. We saw that you can rewrite code securely, and that's a very important ability. And then also, we could use GPT to rewrite legacy code in newer security-focused frameworks. So there are these frameworks like the Rust programming language and the capability hardware model called Cherry, which is a more secure way of handling pointers on machines, but requires code to be aware of the capabilities and to handle them correctly. And therefore there's a huge job now that computer scientists face of rewriting all that legacy code, the Windows operating system, the Linux operating system, and masses of code into these security-focused frameworks. Well, GPT could help with that if trained appropriately. And therefore that's a huge benefit for computer security. Another thing, I think, is that GPT can help explore and understand legacy systems. So the world is full of legacy systems where the authors have died or retired or gone away or lost interest, and people don't understand how those systems are working. GPT could help us understand those and hence manage those legacy systems better. Then another example of how GPT could help defenders is in generating attack scripts, for example, for penetration testing and other kinds of testing. Okay, but most of those things will apply to attackers as well. For example, GPT's ability to write software can be used by attackers to write attack scripts and malware and all kinds of other things. GPT could help attackers write phishing emails. GPT could generate malicious or not even necessarily malicious, just annoying audio and video, could kind of fill the world with this kind of either malicious or just stupid stuff. GPT could automate Twitter bots and other social media bots. That would be a bad thing. And then GPT could automate conversations with victims, like social engineering attacks where an attacker convinces a victim to behave in a certain way. That convincing might involve sending the victim messages and persuading them to do stuff, answering their queries. At the moment, that's mostly done manually. GPT could automate that and hence enormously improve the ability of attackers to launch those attacks. Now, you might think that the censorship jail that ChatGPT has would prevent it from doing these bad things. And indeed, that is part of what it tries to do. It does want to prevent GPT doing bad things. But that's likely to be ineffective in the long run for two reasons. The first is that you can break out of that jail. And there's many articles that you can find, blog posts and so on, where people say, well, if you ask GPT or ChatGPT the question in this or that way, then you can convince it to give you an answer that the censorship jail was designed to prevent. So the first way is that you can break out of the jail. And the second way is that, of course, people will make language models and systems like ChatGPT that don't have a censorship jail. Attackers will make their own version of ChatGPT and it will be designed to enable them to do the things that they want to do, not to prevent them from doing it. So while I think that the censorship jail is a useful thing to have, I think in the end it's likely to be ineffective. Okay, let me now in my last couple of slides turn to consequences for society. Well, I don't need to say much about this. It's going to automate a lot of boring tasks. It's going to make writing tedious text much easier, and those of us like me whose jobs involve writing tedious text, whether it's grant applications or reference letters or whatever, GPT can make that much easier. It can make programming much faster and more fun. And in general, I think GPT is going to make things happen. It's going to enable people in all sorts of ways and make the world go faster. I don't know if that's what you want, but I'm sure that that's what you're going to get. But now the bad consequences are, of course, that there will be short-term loss of jobs. So every technology can bring about loss of jobs, but in general, technology also introduces lots of new jobs. So I do think this is just a short-term loss of jobs. In the end, we'll have as many jobs as we want, as we have right now, even though we've had a lot of technology that has resulted in short-term loss of jobs. You know, at the moment there are more jobs than there are people to fill them in the world. It can vastly increase the amount of bullshit in the world. Well, that's a bad thing. That's just a consequence of making writing text easier and creating videos easier and creating pictures easier and audio and so on. It will amplify fake news, conspiracy theories and echo chambers. Unfortunately, that's just a consequence of what it will do. And for the reasons that I gave, that bad people only have to be right a few times while good people have to be right all the time, GPT is a bit on the side of bad people, and therefore it will boost crime and nefarious activity. So that's bad. But those consequences, I think, are relatively manageable. Some people have expressed much bigger concerns, like the authors of this letter, a letter that asks to pause giant AI experiments. It's an open letter signed by 18,000 people, or nearly 19,000 people here, including Elon Musk, and then Yoshua Bengio, who's an ACM Turing Award winner, and then Yuval Noah Harari, who's a well-known author, and as I say, 18,000 other people. And that letter says that we risk flooding our information channels with propaganda and untruth. Now, as I go through these, let me just tell you what I think about each one. So this one I agree with. I agree that there is that risk that we will do that. I already mentioned that in the previous slide. we risk, according to the letter, automating away all the jobs, including fulfilling ones. Well, I disagree with that. I think that we will automate away some jobs, but we will introduce more fulfilling jobs. And therefore, in the long term, this is not a problem, although it's a problem maybe in the short term and can be addressed in a short-term way. The letter says that we risk producing non-human minds that might eventually outnumber, outsmart, and obsolete and replace humans. Well, I think that's ridiculous. I think that the technology that we've just been looking at here is so incredibly far from being able to do that. We've just seen its limitations in all sorts of ways, and there's just no evidence at all that I can see that we're anywhere near being able to produce technology that could outsmart, obsolete, and replace humans. Now, maybe we will get to that point, but if we do, I think it will be using completely different technology that we haven't yet conceived of. I think it's as ridiculous to say that technologies like GPT can do this as it is to say that the technologies of the 18th and 19th century, like trains and factories and sewing machines, that they could outsmart humans. Because I think that the ability to outsmart humans is so far away on the horizon. And if you play with this technology, you just realize quite quickly how limited it is. And this is true of all the AI technologies that we have today. So that's ridiculous, in my opinion. And then the last risk that they talk about is the risk of losing control of our civilization. Well, that's ridiculous as well. I mean, first of all, civilization is not something that anyone controls. No civilization has been controlled by people or groups of people. Civilization is like an emergent property out of the behavior of all of the people involved in it. And of course, our civilization will end. There's no doubt about that. Partly I say that, my evidence for saying that is that every other civilization that humanity has known has ended. And we already know the big threats to our civilization. They are things like global warming and nuclear weapons escalation. And we know that we're getting closer to that point, and it's just a fact. I don't think that AI is anything like as big a threat as those things. I don't think it's a threat at all. It does have some undesirable social consequences. Those are the ones that I mentioned on the previous slide. But losing control of our civilization just doesn't make any sense to me, because civilization is not something that anyone has ever had any control over. And then finally, the letter calls for all AI labs to immediately pause for at least 6 months the training of AI systems more powerful than GPT-4. Well, I'm saying that's ridiculous as well. First of all, if the problem was as big as they claim, then 6 months is just a drop in the ocean. It's like saying I'm going to put out a forest fire with a bucket full of water. I mean, it's just on the wrong scale. But above all, there's also something kind of stupid about the idea that you could call on AI labs to do that. I mean, do you think that AI labs in China and Russia and North Korea will respond to this call? I mean, that's just not how the world works. I just think that it's the wrong sort of thing. So I do think that there are social problems that have to be addressed and regulations that have to be introduced. But the idea that you could pause things for 6 months is just a stupidly short period and a naive request to make, and therefore consider that to be ridiculous as well. Anyway, thank you for listening to my personal opinions there, and also to my account of GPT, how it works and what it's good for. Bye-bye.